All right, so last week I posted a video of kind of how to set up the machine, the little XMT welders, how to do a basic shielded metal arc weld. If you hadn't had a chance to look at that video, I'm going to repost that in this week's assignments. But we're also going to talk a little bit about some of the different welding positions, some of the joints that we have, and then we'll kind of cover a little bit of that shielded metal arc welding. In lab, we're going to go over how to evaluate the welds, so you'll be able to kind of see that stuff as we go through. Too far. So when we're welding, there's a couple different positions, and typically what we have is you have a weld sheet that has 40 different welds, cuts, different things that you need to actually complete by the end of this semester. Obviously, this is going to be a little bit different this semester, but we're still going to kind of cover the same kind of concepts, so that way we understand, the basic principles of welding. The first one that we want to kind of understand is that anything with a 1 next to it. So if I have like a weld designation, and I say, in the example up in here, it's a 1F weld, that is a weld that is going to be done in the flat position. Meaning that it is flat on the table, the weld, no part of the weld is like raised up, it's not horizontal, you're not welding in a vertical position, so you're not going up, you're not going down, it is literally in a flat position. This is exactly what you saw in that welding video, just kind of showing you how to strike an arc and how to get some of those things kind of situated. So 1F is the easiest type of weld. We have a G and an F, okay? An F stands for a fillet weld, a G stands for a groove weld. On the video, we actually did a 1G weld where we had 2 pieces of metal, we're welding them together. A stringer bead would also technically, I guess, be a 1G weld, although those are just more for practice, understanding how to run the rod. So the 1 position, if there's anything with a 1 designated next to it, it's going to indicate that it is in a flat position weld. If there's a G, that type of weld that is going to be ran is a groove weld. Okay, and we'll go into some of the examples of what it is when we talk about the joints, I think on the next slide. If there's an F next to it, it stands for a fillet weld. Notice on the G, it doesn't matter if it is in 2 pieces of pipe, it is still a groove weld if you're joining the pipes together, not when we're layering like 1 piece of metal on top of another. If you have any designation of a 2, that 2 is going to indicate that it's in a horizontal position. You'll notice right here on this top example where it says 2F, okay, this is a fillet weld because there are 2 pieces of metal that are coming in, but notice that just because this piece is flat doesn't mean your weld is. This piece right here is going horizontal, and so if you're making a weld, this thing could be flat on the table here, but because that piece is vertical and we're trying to fill this weld in that area, that is designated as a horizontal position. For that same joint to be a 1 like this, both those pieces would have to be, kind of turned on its side, kind of a 45-degree angle, and that weld would actually be flat with the earth. So it really has to do with the gravity and how gravity takes effect on that weld, depending on the position. And there's different things that we're going to do as we're welding, depending on are we fighting gravity or is gravity just grabbing it and pulling it down right into the weld. So they get progressively harder as you go through these different joints. You'll notice a 2G there if we have 2 pieces of metal that we were just welding together using a little groove weld. That one is going to be upright in the horizontal position, and you're going to weld across from left to right or from right to left. It doesn't matter which direction you run. It's still considered a groove weld if it's horizontal, if you're essentially flat with the earth and you're running it flat with the earth, at that same angle. A 3F is going to be a vertical position. It does not designate whether it's a vertical up weld or a vertical down. You can weld in both positions. But if it's an F, it's going to indicate that it is if it's a 3, it's going to indicate that it is a vertical position. Notice how this metal kind of turns up. Again, you can be welding up, you could be welding down, doesn't matter. Same thing for the groove welds. This right here where it says 5G, that is a different thing. We'll talk about that in a minute, okay? So these ones are all 2s, okay? These ones are 3s. This is a different category. The last one that we have, well, the last one of these kind of standard ones is a 4F and a 4G. That 4 indicates that it's going to be in the overhead position. So this weld would be up above your head and you're welding upside down trying to complete that weld. Again, gravity is going to affect these things a little bit, and so you're going to have to take that into account when you're welding. These ones, between the 3s and the 4s. 4s are actually not that hard. What's hard about that is keeping your hands up in the air because the blood flow, your heart has a hard time pumping that blood, and your hands won't, want to stay up. The 3F really gets a lot of heat, really gets a lot of penetration, but because of that, it melts that metal and it wants to just drop out and not hold that weld in place. The vertical positions are some of the harder ones, especially vertical ups, but there's some benefits in the penetration and how much strength you have if you could do them correctly. So the 4 is overhead. It's important for you to understand that. Now the 5G and the 6G, these ones are related to pipe only. And in the 5G position, why this is different than a 3F and a 4F, why it's different than a 1G. Okay, a 1G, I can rotate that pipe around. So if it's on like a little turntable, it can rotate that pipe and I can weld while that pipe's turning. I can basically just hold my rod still and I can weld all around that stuff. So everything essentially could be done on the very top, and as that pipe is spinning, that weld is just being completed. In the 5G position, it is stationary, so the pipe cannot move. And this is where we really start getting into some certifications of stuff, where people get certified. They get certified in a 5G or they get certified in a 6G, and it kind of qualifies them for everything else. And the reason that qualifies them for everything else is that 5G weld has both flat position, it has verticals, and it has overheads. Okay, so it's kind of a combination kind of all of those kind of together. A 6G, very similar, it's in a stationary position, but it's on an angle. Okay, and that angle makes it even a little bit more difficult. So sometimes when we go and people get certified, especially, pipe welders that are going and they're putting stuff together for processing plants and stuff like that, they get certified in those pipe welds. If they get certified in a 6G, they're going to be able to do a 1G, a 2G, they'll be able to do a 5G, because if you can do the most complicated one, they pretty much assume that you can do the other ones as well, because those components are kind of mixed in with that singular weld. Now, a couple things on certifications. One, just because you're certified doesn't mean you are going to be able to weld anywhere you want. Okay, you have to get certified. You have to retest on certifications. You have to show that you are, maintaining. You have so many hours, doing that type of work to be able to maintain that certification. If not, you're going to have to get recertified. So it's not a one-time thing and you're done and you're good to go. On the other merit, just because you're not certified, it doesn't mean that you can't weld on things. For example, any one of you could build a trailer in this class. You could build a trailer or out on your own. Okay, you can take it to DMV, you can get it registered. They're going to look at the axle ratings and they're going to put a GVW sticker on there that says this trailer is rated at this weight, and you can drive that down the road legally. There is nobody that's going to inspect that. There's nobody that's going to say, nope, you can't have this thing. There's no qualifications. There's no certifications. There's nothing that goes along with that. Now, if you are driving a trailer down the road and it is unsafe or unfit to drive because you welded it up and it was not a good quality, a police officer could pull you over and he could fine you for like an unsafe load or something like that. But there is no qualifications, which is a little bit scary sometimes, but it also kind of opens up, opportunities for people. Certifications aren't necessarily the end all be all. You don't have to get certified. In fact, a lot of things, a job will certify you for that particular job on that particular site. And if you go to a different site, you're going to have to get recertified, even though you may have done that if it's at a different site. A lot of common misconceptions. People think certifications are like you get it, you're done, and that's it, and you're good for life. And it's just not the case. That's not how it works. We're not going to focus on certifications in here because most of you guys, if any of you, probably aren't even going to be welders at all. So it's not something that we're going to focus on. That's something that community colleges typically are going to handle because they get a lot of students in their programs that they want to be welders and they want to get hired at these places where there are certification requirements. And so they go through those things a little bit more in depth. But it's good to understand just a little bit about that. So when we're welding, there's a couple different joints. Okay, we talked about types of welds. We talked about fillet welds. We talked about groove welds. Those are the two main types of welds that we're going to make. Now, in between those things, there's also the joints. And that basically is how does the metal line up with each other? Because obviously when we're welding, the purpose of it is to join two pieces of metal together or more, if that, depending on what kind of project you're building. But in this class, it's a practice course, right? We're going through welds we're trying to understand how to weld, we're trying to understand how to evaluate welds and how to look at them. So it's important to understand the joints and the different types of joints that we use. Butt joints, probably, one of the easiest ones to kind of do. It's very common. You got two pieces of metal, they're side by side, and you make a weld bead right down the middle. Lap joints are when we take a piece of metal and we actually offset those things. So one piece is sitting on top of the other piece. The welds that are done in here, because we're filling in this little kind of triangle gap right there, it's called a fillet weld. This one, we're actually filling in a groove or a gap in between the metal there. And so that's called a groove weld. Okay. You do see these quite a bit. They're really common. The other ones you see are kind of corner joints. Corner joints and T-joints are very similar to each other. It just has to do with where that metal is placed. Is it on the edge of one piece of metal, okay, or is it in the middle of the other ones? So you can see there's a T-joint, you can see the corner joint. These ones as well are called fillet welds. Those are fillet welds because you're trying to fill in that little kind of triangle gap right there. T-joints, corner joints, those are probably some of the most common welds that you see in most welds on projects and different things. That's what they're going to consist of. You do see laps, you do see butts, and very often do you see edge joints, but edge joints are when we have two pieces coming together. Sometimes it's going to have a flange where it's going to kind of flare out, and you just want to weld those. This is going to be considered a groove weld, just like a butt joint. We actually aren't going to mess with any of these things here because this is one that you see very, very little of. And the corner joints and the T-joints, because they're very similar, we really just focus on butts, laps, and T-joints. That way we can get through a lot of stuff because there's a lot of different things that we're trying to learn in here. And so it's important for you to understand that there's these joints. And these are the basic ones, but really these three, butt, lap, and joint, those are the ones that we really want to focus on. Those are the ones that we're going to pay attention to. So when we're welding, if you watch that video, I think we talked a little bit about the different types of rods. Okay, we have a 6011 rod, we have a 7018 rod, and there's a couple things we want to go through about those because those numbers actually mean something. So if you see those numbers, I want you to understand what that stuff is. On your midterm, you are going to get tested on these numbers here, and I'm going to explain them. You're going to have this PowerPoint. It's posted up on Canvas. You'll have this video that you can look at and rewatch if you need to. So the E6011, the E7018, two very common rods that we use in the industry. They have different purposes from one to the other. Both of them have the letter E. It just stands for electrode. Okay, it's just kind of a simple thing. Don't overcomplicate it. It's a welding rod or it's an electrode. It's, kind of another term that we use for it. Now these ones have a 4-digit code. Okay? So after that E, right, we're going to have 4 digits. Some rods are going to have 5 digits on them, and I'll explain the difference in those in just a second. Okay, but in a 4-digit code, the first 2 numbers are going to represent the tensile strength. Tensile strength has to do with how much force it takes to pull those things apart. Okay, how much force it takes to pull them apart. So they actually put this metal in clamps and they pull them apart and they record the strength that it takes to pull them apart. And those first 2 numbers are going to represent that tensile strength. And it's going to be in, I think it's thousandths of a pound. So if you have a 60, it's 60 thousandths tensile strength, or PSI, 60,000 pounds per square inch. So if that rod was a square inch, okay, it would take 60,000 pounds of force to pull those things apart. Really strong, has to meet those ratings. 7018 rod, going to be the same thing. It's a 70,000 pound tensile strength rod. So the 7018 has more strength than the 6011. We use the 6011 because it works on dirty, greasy, painted metal. It works really good to cut through that stuff and still get good welds. 718, even though it's a stronger rod, it can only really be used on like cleaner metal. If you got a lot of rust, if you got a lot of paint and other debris, it just doesn't eat through that stuff as well as a 6011. So if you're doing repair work, 6011 is a pretty good rod. If you're doing kind of new construction and areas where you really want strength, 718 is going to be a better rod for those things. If you have a 5-digit number, the first 3 numbers are going to indicate the tensile strength. So if I have a 118 or 10018 rod, it's going to be 100,000 pounds of tensile strength. So really high quality, great stuff. When we really need that strength, you might see that in like skyscraper construction or real tall buildings. Anything where strength is of the utmost importance, you're going to see that. But again, the most common rods you see, 7018 and 6011. Okay, Okay, and those are the two rods that we're going to focus on in this class. The second to last number or digit refers to the welding position. So this is going to be whether we talked about that one position being a flat, whether we talked about the 2 being a horizontal, the 3 being a vertical, and the 4 being an overhead. Okay, these numbers do not correlate with those. Okay, but on that rod, if you have a 1, you can use those in all of those positions. So you can run it in a flat, a horizontal, a vertical, and overhead. It doesn't matter. You can do a 5 or a 6 even, because obviously those are the combinations, right? So if there's a 1, it's all positions. Both of these rods you can run in any position. It doesn't matter. You can run them overhead. You can run them vertical. If it's got a number 2, it's going to be for flat and horizontal welds only. So you cannot do verticals, you cannot do overheads. Typically those rods cool a lot slower, and so the metal stays molten for a longer period of time. And then what happens with that is that metal will start to drop out, especially when we doing like vertical ups and the overheads. Gravity is going to take effect, and it really affects those things. So those rods are really designed to run in a flat and horizontal position only. And then you have a number 4 that you're typically, that you may see, and that's going to be something that's going to be run in a flat, horizontal, vertical down, or an overhead. Just no vertical up with that. Vertical up is one of the toughest welds that you can make. And the way that these rods are ran, the way that they're designed, that metal is just going to fall out of there, and you're just not going to get a good quality weld. So you do see, 1, 2s, and 4s. I don't know why they skipped 3. This is the AWS, the American Welding Society. They made these classifications, and I have no idea why they skipped a number 3. Maybe they had it, they deleted it, and that was left. But these are the 3 that you see most often. You're going to see a 1 in that second to last digit position, and it's going to just indicate what position you're going to be welding in or capable of welding in. The last number, kind of in combination with the second to last number, is going to indicate the coating that you have and the correct polarity that we have on this. Now, I am not going to require you to remember this list right here that we have here. Okay, I don't remember it. I don't care to remember it. If you need to reference it, there's a table, you can reference it, and so you know. If you watch that welding video, we talked a little bit about DC electrode positive and how we set it up. Some rods run in DC electrode negative, some run in alternating current or AC current. It just depends on those digits of those rods and what we can run. It also tells you whether or not we have a high coating, like a cellulose sodium or a cellulose potassium. Those things, I'll explain that in just a second, okay? But the biggest thing that I want you to remember, and this is what you're gonna get tested on, is that last number is used to determine the coating and the correct polarity. Again, you don't need to memorize that table, okay? But you need to memorize that last number is type and coating. What you should do, and I'm gonna go back, you should know what the 1, 2, and the 4 means in the second to last digit. If I give you a question and it says, hey, it's a 70-24 rod, okay, that second to last digit's a 2, you should know that rod is going to be ran in flat and horizontal positions only. Okay, but I do not expect you to memorize this list here. Just understand that it's the type of coating and the polarity. So the polarity, right, it's going to be AC/DC. If we have a 60-11, 70-18, the last digit's a 1. It's a high cellulose potassium. It can be ran in any polarity. Okay, there's really 3 options that we have. 70-18 ends with an 8. That one, again, it's a low hydrogen potassium iron powder that can be ran in all 3 different types of polarities as well. We typically run in DC electrode positive because it's going to get us the most penetration, the most burn through, and we're going to get a better quality weld typically out of that. Especially on thicker metal, those are that's kind of really what you want to run into. Now, that 70-18 rod is what we consider a low hydrogen rod. And hydrogen in a weld is a bad thing. We don't want those. We actually store these 70-18 rods in an oven to prevent ambient moisture from collecting in those rods and then destroying our weld. We're going to get a thing called porosity. When we start talking about evaluating welds and different things, we'll see some of that porosity. I think this PowerPoint has a little bit of that. And then when we go into lab and we start talking about evaluating, I'll show you what that looks like as well. Hopefully I can find some examples in person. So when we're welding, you're going to have a little iron core, okay? And that's going to be the thing that has the tensile strength that's going to create that strength of that welding electrode. for us. There's also going to be a coating on the outside, and that coating is what we call our flux. That flux is going to create a nice little shielded gas or a shielded atmosphere that's going to protect it from, the oxygen, nitrogen, and hydrogen in the air from actually penetrating it. When we melt this metal, we basically make this metal vulnerable. And if we get an inclusion of, foreign debris, or we get, that oxygen, hydrogen, or nitrogen in there, that's what's going to end up giving us porosity. It's basically holes that are developed in there from those gas molecules getting trapped, and then it's going to weaken that weld, okay? Sometimes it's on the inside and you can't see it. Sometimes it's very obvious it's on the outside, and it's got a bunch of holes in it. It's melting. If you're doing a good job, it's going to be melting that base metal, and it's joining that new metal that you're introducing from your rod, and it's joining those into one solid piece. How far we get in our depth of penetration, you can kind of see right here. If the original metal is here, it melts that top layer away, and then it adds that metal into there. The more we get, or the deeper we get into there, the stronger that weld is going to be. If we only hit the top layer or the top surface, that weld may look really good, but it's not going to be very good. And I do have some examples somewhere that I will try to show you in lab, so that way you can see that stuff. When you're done with these welds, what's going to happen is that flux that is burning away and creating that atmosphere is also going into collecting and creating a little jacket that goes on top of that weld. And that jacket needs to be chipped off. It needs to be cleaned off if you're going to make another weld on top of that, or even just when we're done with it, we've got to clean off that slag that's going to be on top. That slag is going to have impurities that are on the inside. If there's anything in the metal, if there was some like grease, if there was some rust in there, it's going to help kind of float those things to the top. So that way that metal that you have underneath is pure mild steel, if that's kind of what we're running with. 6011, 718 is a mild steel rod. So that electrode, you got to understand that it is consumable. It is going to burn, okay? It's going to form that little molten puddle. And in that video, I think we have a pretty good capture of what it's supposed to look like, but here's an example for you so that way you can see. This area right here is your molten pool. As you are welding, okay, that molten pool is going to get bigger and bigger and bigger. How fast we move forward is going to determine how big that puddle is. We should be about 1.5 times the diameter of the rod. That's how big that puddle should be. That's on average. It really depends on different welds, but a good rule of thumb is 1.5 times the thickness of the rod is how wide your pool should be. You're watching that pool when you are welding, okay? That's where your eyes should be. That's where you should be looking at. That's how you know, where's my speed? Where's, this stuff? We talked about arc gap in that video. That arc gap has to be a certain distance, otherwise that pool doesn't start to form. It'll spread metal all over the place. And when we talk about evaluating, those are going to be the things that we're going to see after the fact that we can kind of determine what happened while somebody was welding, okay? The shielding gas, okay, we talked about that. This is an example right here in this picture. That is porosity. That is, you're getting nitrogen, you're getting oxygen, and you're getting hydrogen that's forming in there, okay? So that flux that, is melting creates that shielding gas. It protects it from those, that stuff in the atmosphere. The low hydrogen rod of the 7018 helps prevent water or moisture from getting in. That's got oxygen and hydrogen as it starts to break down. So we don't want that moisture in there because we will introduce that into there. That flux isn't going to be effective. So that's why we store 7018 rods in an oven, okay? The idea is to get those things to float to the top, keep them from getting into there, and that's really what that shielding gas and that flux does. If you clean off your metal, it's going to be better. You can kind of see in this image where they kind of ground down. They may have some other issues. I'm not even sure if this is shield metal arc welding, but if they grind down where you work and you get this mill scale, you can see kind of this gray kind of stuff. That's called a mill scale. As it goes through the manufacturing process, metal will have kind of impurities kind of float to the top, float to the surface. And that's what this is. On very standard, when you see metal, mild steel, you'll see this kind of like dull kind of gray color on there. And that is just what we call a mill scale. It's from the factory. When they manufacture that, it gets that. If you want to have a good quality weld, grind that stuff off completely. At least in the weld area, you need to grind that off. So that way you don't have any of those inclusions. A lot of times, especially like a 6011, it'll burn through that. It'll float those to the top. You're not going to get that porosity in there. But if you want to fine tune it and you want to make your welds good, cleaning is the key. And certain processes, cleaning is even more important. Once that metal, went too far. Once that pool is cooled down, you've got that joint between those two pieces. You're going to have that slag that's going to be done. That's going to be chipped off, but it's just kind of a jacket that's covering it. And if you do a weld properly, the base metal or the weld itself is going to be as strong as the base metal. Okay, if it's done properly and you get the penetration that you need, and everything is done right, your speed and all those kinds of things, it will be just as strong as the base metal, if not stronger. Okay, that's the idea. That's what we're looking for. That's the goal. So that slag, right, we've talked about that. It's going to float, any kind of impurities that are in there. As this stuff is melting, this metal is melting. Again, we're doing this, it's creating about 9,000 degrees Fahrenheit. So it's hot. It's creating a lot of heat with this stuff. And what you want to do is you want to kind of float any of those things that, as it's kind of just creating this little melting pot, you want those things to come up. A 6011 rod is what we call a fast freeze rod. And that means that that weld solidifies rapidly. Now there's some advantages to that, okay, is that those impurities kind of float up to the top, really quickly. But what happens is if you make a mistake, if you bump it or you do something or you're, a little bit fast, it's not as forgiving as a 7018 rod, which has a slow cooling effect. It will, that, weld jacket or that slag that covers it is a little bit thicker. It helps kind of insulate that. It makes that weld, stay molten metal for a longer period of time. We're not talking like a whole lot. We're talking, seconds, but seconds make a big difference in there. So that 6011 is a good rod for training because you can make a mistake, you can do those different things, and we can see those examples. Again, when we start going through and evaluating, you're going to get a good idea. And that's really kind of one of the biggest things we're going to work on this semester is, can you identify a good weld versus a bad weld? And what can you tell me about that weld? What happened during that weld? Where can we make those corrections? And that's really what we do if we were in lab. You would go weld, we would look at it, we would evaluate it, and you would try to correct those mistakes that you'd be seeing. Obviously, we don't have the ability to weld, so the next best thing is really just to evaluate these things. There's a little crater that kind of forms at the end. I don't have a picture of it. There's a little crater that forms at the end of these things, and typically what happens is as you're pulling that rod away, it just kind of blows out that metal and it kind of creates a little divot at the end of the weld. You can do this by, when you're welding, taking the rod and kicking it back the other way real quick and kind of filling that in. You can do it by snapping out of the puddle where you basically just pull out, or you can kind of slow down right at the end, lower that arc gap, okay, and then pull it out. And those are going to be some ways that you can kind of fill that in. What you may see at the end of that weld is cracking in that crater because typically it's going to be a little bit thinner than the rest of the weld, and you might see a crack start to form. If you see any cracks or if you see any holes in metal, that is a bad thing. We do not want to see that because that crack is then going to fracture the rest of that weld. Okay, you think about like a chain, the chain is only as strong as its weakest link because every link has to be as strong. A weld is really the same way. If there's a weak spot in that weld, it's going to cause the rest of that weld to fatigue and then fail on us down the road. And ideally, we don't want welds to fail. Sometimes, and a lot of times, people's lives depend on these things. That's why sometimes we have these certifications that are required, and sometimes they're not required, but we want to have that good practice of putting a good weld down to make sure that people are not going to get hurt. So I know that's a lot of information, but again, you're going to have this video, rewatch it if you need to. If you have any questions, you can ask me in lab, but we're going to go over lab evaluation stuff.